So now that I've given you a quick overview of what safe publication is in general and talked about how you have to properly construct objects and you have to make sure that their state, their fields are correctly and safely published, let's take a deeper dive into different safe publication techniques that you can leverage in Java. And as you'll see, there's a bunch of different ways you can have multiple threads share an object and its state safely. So again, just to kind of recap, if you have a properly constructed object and you want to publish it safely between multiple threads, here's the things that you have to do. You have to make sure that the reference to the object and, perhaps more importantly, the object state are made visible to other threads at the same time. It's not sufficient just to have the reference to the object visible, because if its state hasn't caught up with the reference, then you can have another thread access the state incorrectly because it hasn't been published yet. So you can publish the object safely in several ways. One way to do this is to store a reference to it in a field that's protected by a lock. So this is kind of the classic way of doing things. And just to make the example interesting and build on itself, we're going to use an example here of a thread-safe singleton. Hopefully you're all familiar with the good old singleton pattern from the Gang of Four book. Remember, the singleton pattern's intent is to allow only one, or to ensure there's only one object of a class, and that object can be accessed by different parts of the program. So it's basically a way to get access to global state without requiring global variables. So one way to ensure thread-safe singleton would be to just wrap its instance method, because instance is how you access a singleton, because you can't make an instance yourself. You have to access it through the instance accessor method. Just wrap a synchronized statement around the code in the instance method of the singleton. So you see that that's a static method, and you can see that we synchronize on the singleton.class field. Every object in Java has a class field associated with it that keeps certain metadata about the class that's useful for things like reflection and so on. So that's one way to do things. That will ensure that all the state is properly pushed out, because of course that's the side effect that occurs when you use synchronized statements or synchronized methods. So what'll happen here is when the inst field is updated, the state of the singleton will also be updated and propagated to other threads. So we're kind of propagating or publishing the reference and the state, and we're doing that by using the synchronized statement here. The downside with this approach, and why you might want some other more optimized way of doing safe publication, is that every call to instance is synchronized. And we don't actually need every call to instance synchronized. We just need the call synchronized that initializes the singleton the first time in. So what we're going to do now is we're going to take a look at another way to do this, which is a little bit lighter weight than having to synchronize the entire instance method. And this is going to be done by storing a reference to the state, storing a reference to the object which contains the state in a volatile variable. So let's take a look. Here's how you can do this approach. This uses a feature that came along in later versions of Java. We'll talk more about that. And the reason it was added to Java, I think I mentioned before, was because in 1997, I wrote a paper talking about the double-checked locking optimization pattern, which became very popular. But unfortunately, at the time, Java didn't support the double-check locking semantics in its memory model. So they added support for that in Java 5. And the way it works is you indicate something is going to be a static volatile, as we see here. And then by putting that type qualifier on the field, it would ensure that multiple threads would share the singleton instance correctly if you followed the appropriate usage pattern in Java. And here's what it looks like. The first time in, you check to see whether or not that field is null. And then, and only then, you synchronize on the singleton class, so that when you double check, when you come in and say, is result still equal to null? That's the lazy initialization check. Then and only then you do the initialization of the singleton once and only once. So we only will go ahead and acquire the lock in the synchronized statement one time, and then we double check to see if we've already initialized the field? And if so, we just go right through and release the lock. If not, the first time in, we go ahead and allocate the new singleton. So using volatile here avoids problems with partially constructed objects. So we make sure that the object is completely constructed and its state and its reference are properly published to any other threads that want to be using this singleton in the context of a multi-threaded program. And then the last thing on the way out, we return the result, which should also be consistent and published properly to all the other threads in a multi-core solution. This approach works fine. The downside is it only works if you have Java 1.5 and later, because the first versions of Java didn't support this until I wrote that paper, and then people started to talk about it. So the downside is it's not portable to older versions of Java, which honestly don't really matter for the most part. But if you're stuck with a very early version of Java, then you can't use this technique. Another technique that you could use, although this won't help you either because this feature was added in Java 1.5 as well, is to store a reference in an atomic reference. So here's an example that shows how to do this. So this is another way of implementing a thread-safe singleton that doesn't use volatile. What it does do is it creates a static atomic reference. And in this particular case, we have our atomic reference, and then we use the get method on the atomic reference, which will atomically get the value. And we check to see the first time in, the value will be null. And what we do then is if it's null the first time in, we make the new singleton. And then we use the compare and set operation on atomic reference to atomically update the singleton if and only if the current value is null. So that will only occur one time, the first time in. And then we go ahead and we get the value again, just so we have it. And we return that as the result here. So that's another way to do it. The problem with this approach is that the singleton's constructor can be called multiple times. If multiple threads just happen to show up at exactly the same moment and the atomic reference hasn't been initialized, then what you'll see is the first thread will call the constructor, do the compare and set, and then the other threads will also call the constructor, and then they'll get the updated value. The downside, though, is if there's side effects in the constructor, then obviously that's going to have some problematic effects. So this approach isn't quite as clean as the singleton approach, but it's another way to do things. Yet another way to do it, which will actually work with the earliest versions of Java, is to use the initialization on demand holder idiom. And you can read about that idiom if you take a look at the link down below. And this idiom relies on the semantics of initialization within a Java execution environment, such as the JVM. And what we're doing here is we're having this thing called the lazy holder, which is a static class, and it has essentially a static final field called sinst. And this initialization will take place the first time when this class is brought into the program. And it's also done in a thread-safe way. So lazy holder, the initialization of this, is only initialized when the static method instance is invoked on the class singleton, which will then trigger the Java virtual machine or whatever the execution environment is to load and initialize the lazy holder class. So this is yet another way to do safe publication using clever techniques. There's yet other ways of being able to do safe publication. You can store a reference to an object into a final field. And this is a very popular technique we'll talk about in a second, based on what are called immutable objects. So here's basically the way this works. If you have final fields, they can be accessed without requiring any other form of synchronization, because final has certain semantics and certain guarantees on it that work nicely to ensure that objects will properly be propagated throughout the system. So as you can see here, if we define ourselves class A and thread T1 will make an instance of class A, and then thread T2 will say a.mFinal, then it's guaranteed that it'll actually read the value of mFinal, because that was initialized when the system was created or was being brought into its initial state. And so you're fine. However, if you try to access a.mNotFinal, no guarantees are made because it's not a final. So it might not be properly propagated throughout the memory hierarchy in that case. Now, it turns out that there are certain classes in Java that are designed around the concept of immutability. And so they work perfectly fine when shared between threads. So a good example of that, of course, is the string class, where you have only final fields and only essentially accessor methods. There's no mutator methods. There's no non-final fields. So string can trivially be shared amongst threads, and you don't have to worry about the inconsistencies that might otherwise occur because it's based on final. And you can learn more about why string is immutable in Java if you take a look at this link down below. Now, here's another little bit of trivia. If a final field refers to a mutable object, you still need synchronization to access the state of the referenced object. And this is very subtle. So before we saw that we had a final field that was essentially a primitive, so everything was fine. Over here, however, we're going to see a slightly different example. So in this case, we have a final field that's an array of strings. And so we call them QBs for reasons that will become clear in a second. And this is initialized to be an array with a bunch of names of famous NFL quarterbacks like Tom Brady, Brett Favre, Cam Newton, and so on and so forth. And then down here, we're going to see how we create a new instance of A, and then thread T1 is going to access QB's sub 1 and store the value Manning in there. And thread T2 is going to access array element 1 of QB's and store Montana there. And if you don't use the synchronized keyword here, if you don't have a synchronized statement, then all bets are off in terms of what happens, because even though QB's is final, the state that it refers to is not final. So in order to be able to make sure that that gets propagated properly, we need to wrap it with synchronized statements or some other synchronizer like a reentrant lock or whatever else we might want to use. So that's the end of the overview. It walks through a bunch of examples of safe publication techniques in Java. Quite frankly, the easy way to do this is just to use the appropriate synchronizers, either synchronized statements, synchronized methods, reentrant lock, whatever. That will make your life very simple. It's only when you need to start getting very clever that you might want to use those other techniques we looked at, like the volatile variables or the atomic references or the other techniques that we looked at, like the lazy holder approach. But that's very, very specialized. And so by and large, you're really well off just to stick with synchronizers in order to make sure that things are properly synchronized and properly published safely in Java multi-threaded programs.